Hello friends, I welcome you in lecture number 17 on complex integration. In this lecture we are going to discuss about Cauchy integral formula. We will see that how we can use Cauchy integral formula in evaluation of certain type of contour integrals. So first we understand what is Cauchy integral formula. So for Cauchy integral formula we require a function denoted by f of z which is analytic everywhere inside and on a simple closed contour C. Suppose we have a function f of z which is analytic everywhere inside, that is at all points interior to this simple closed contour as well as on the boundary of this simple closed contour. Then Cauchy integral formula says that we have 1 divided by 2 pi I integral of f of z divided by z minus z0, where this z0 is a point which is interior to this simple closed contour, and this integral is given by value of this function f of z at point z0 which is inside this simple closed contour C. I repeat again, suppose we have a function which is analytic everywhere inside and on a simple closed contour C, and we have some point z0 which is interior to this simple closed contour C. Then value of this integral 1 over 2 pi I integral of f of z over z minus z0 is given by value of this function at point z0, and that is along this simple closed contour C. This we can rewrite as integral of f of z divided by z minus z0 along simple closed contour is equal to 2 pi I times f of z0. So using Cauchy integral formula, if our contour integral can be written in this form, that f of z divided by z minus z0, where this f of z is analytic everywhere inside and on a simple closed contour, and this z0 is interior to this simple closed contour, then in evaluating this type of integrals we can apply Cauchy integral formula. So this integral is equal to 2 pi I times value of this function f of z at point z0, and we will remember this Cauchy integral formula. We are not going to prove this, but we are going to use this Cauchy integral formula in evaluating certain type of contour integrals in which our function which we want to integrate can be written in this form. Which form? F of z divided by z minus z0, where this f of z is analytic everywhere inside and on a simple closed contour, and this z0 is a point which is interior to given simple closed contour. So sometimes they can ask you to write down the statement of Cauchy integral formula. You should write systematically. Here I have written as a theorem. Suppose that a function f is analytic everywhere, that is at all points inside and on a simple closed contour C, taken in positive sense, that is in counterclockwise direction. If z0 is a point interior to simple closed contour C, then value of this integral is given by value of function f at point z0 which is interior to this simple closed contour, and using this formula we can evaluate contour integrals of this type f of z divided by z minus z0, and it is given by 2 pi I times f of z0. So whenever our contour integral is in this form, we can evaluate it by using Cauchy integral formula. I have taken two examples to explain this. First integral is evaluate sin 3z divided by z plus pi by 2 with respect to z, where C is the circle whose center is origin and radius is 5, taken in positive sense, that is in counterclockwise direction. So you can see here we have to integrate sine 3z divided by z plus pi by 2, and this I can rewrite as sine 3z divided by z minus pi by 2. And now we know that sine 3z is analytic everywhere, or it is an entire function, and therefore it is analytic everywhere inside and on this circle with center 0 and radius 5. And here minus pi by 2 will be interior to this circle. If we take absolute value of minus pi by 2, then it is pi by 2 and it is less than 5. That means modulus of minus pi by 2 is less than 5. Therefore minus pi by 2 is inside this circle, which is a simple closed contour. So we can consider f of z equal to sine 3z, and if we compare with z minus z0, here z0 is minus pi by 2. If we wish, we can visualize geometrically also. Our contour is circle with center 0 and radius 5. So we can roughly sketch that circle in the xy plane. Suppose this is a circle with center 0 and radius 5. Okay, this is just a rough sketch. So this is our circle whose center is origin and radius is 5. So this much distance is 5, and pi by 2 means 3.14 something. So it is somewhere here. The point is minus pi by 2. Okay, if we compare with z minus z0, z0 is minus pi by 2. So we can see that minus pi by 2 is interior to this simple closed contour, and f of z is sine 3z, which is analytic everywhere in the complex plane. Therefore it is analytic everywhere inside and on this simple closed contour. So we can apply Cauchy integral formula by taking f of z equal to sine 3z. So we should write systematically. Let f of z equal to sine 3z, and clearly f of z is analytic everywhere. We know that sine function is entire function, and therefore f of z is analytic everywhere inside and on the circle mod z equal to 5. Because it is analytic everywhere in the complex plane, therefore it is analytic everywhere inside and on the circle mod z equal to 5, and we know that this is a simple closed contour, which is a simple closed contour, and z equal to minus pi by 2 lies inside this circle. Okay, as we have seen that z equal to minus pi by 2 is inside this circle. Okay, that we have seen here. So therefore we can apply Cauchy integral formula. Therefore by Cauchy integral formula, integral over this circle mod z equal to 5, f of z divided by z minus pi by 2 is given by 2 pi I times value of this f of z at z0, which is minus pi by 2. 2 pi I times f of minus pi by 2. Now f of z is sine 3z. So here we have to put z equal to minus pi by 2. Sine 3z, z is minus pi by 2, and this I can rewrite as 2 pi I sine of minus 3 pi by 2, and because sine is odd function, negative sign comes outside, and here I have sine 3 pi by 2, and we know that sine 3 pi by 2 is minus 1, therefore we will have plus 2 pi I. Sine pi by 2 is 1, here we have sine pi by 2 1 and sine 3 pi by 2 is minus 1, therefore integral has value 2 pi I. So what we have obtained, integral of sine 3z divided by z plus pi by 2 along the contour mod z equal to 5 in counterclockwise direction is 2 pi I. So this is very easy formula. You just have to check whether you can write your integral in this form: f of z divided by z minus z0, where this numerator f of z is analytic everywhere inside and on a given simple closed contour, and this point is interior to given simple closed contour. Here our function f of z is sine 3z, and it is analytic everywhere in the complex plane, therefore it is analytic everywhere inside and on this circle, and z0 is minus pi by 2 and it is interior to this simple closed contour, therefore we are able to apply Cauchy integral formula here. So whenever you have any example of contour integrals, you can check whether you can write your contour integral in this form, and you can easily evaluate that integral using Cauchy integral formula. I have taken another integral. Here we have e raised to z divided by z minus 2i, and contour is circle with center 2i and radius 4. So we can roughly sketch this circle with center 2i and radius 4. 2i means we have our center on the y-axis. Suppose this much distance is 1, then this is I, and here I will have 2i, and radius is 4, so this is going to pass through this point here, and here we will have 1, 2, 3 and 4. I have to extend somewhere here. Okay, this is 1, 2, and here radius is 4, so I have to go 4 units above this center as well as 4 units below this center. Similarly 4 units to the right and 4 units to the left. So our circle is like this. Okay, you need not sketch the given contour. This is just for understanding that what is the situation in our hand. So I am just roughly sketching the circle, so it may not look like circle, but you should understand that it is a circle whose center is 2i and radius is 4. So our contour is circle with center 2i and radius 4. So this is 3i, 4i, 5i, and this point will be 6i. Here I have I, 0, minus I, and here I have minus 2i. So now we have 2i here. If we compare this with z minus z0, then we have 2i interior to this circle, and you can see this 2i is nothing but center of this circle, therefore it is obviously interior to the circle. I have sketched this figure just to explain that how we can see that this point is interior to given circle. Otherwise you need not draw this circle. You can just put a value of z0, that is 2i, in this part, and you can check whether your absolute value is less than 4 or not. If it is less than 4, then it is interior to C. If it is greater than 4, then it is outer side of the given contour. So that we can check here also. Suppose I take z equal to 2i here, then I will have 2i minus 2i, that is 0, and it is less than 4. Therefore we can say that 2i lies inside given simple closed contour. And if we compare with f of z divided by z minus z0, if we compare this with f of z divided by z minus z0, then we can see we have f of z equal to e raised to z, which is entire function, analytic everywhere in the complex plane. Therefore it is analytic everywhere inside and on this simple closed contour, and z0 is 2i. So we should write systematically. We can start with f of z equal to e raised to z. So we can write that clearly. F of z is analytic everywhere inside and on a simple closed contour. Our simple closed contour is circle with center 2i and radius 4, and we have observed that the point 2i lies inside this simple closed contour, and therefore we can write that by Cauchy-integral formula, integral of f of z divided by z minus 2i with respect to z along given simple closed contour is equal to 2 pi I times value of this f of z at this point, that is f of 2i. Now f of z we have taken is e raised to z, so I will put z equal to 2i in e raised to z. And now we can use Euler's formula. We know that e raised to I theta is cos theta plus I sin theta. Here theta is 2, so we have cos 2 plus I sin 2. And if we wish, we can simplify this. We can rewrite this as 2 pi cos 2 into I, and 2 pi I square into sin 2, and I square is minus 1, so we have minus 2 pi sin 2, or this I can rewrite as minus 2 pi sin 2 plus 2 pi cos 2 into I. This is real part and this is imaginary part. And if we wish, we can find out values of sin 2 and cosine 2 using scientific calculator, or we can keep this as it is. So it is very easy to use Cauchy integral formula. All we have to check is whether we can write our integral in this form. If our integral can be written as f of z divided by z minus z0, where C is a simple closed contour, this z0 lies inside C, as well as this function in the numerator is analytic everywhere inside and on this simple closed contour, then this is given by 2 pi I times value of this numerator function at point z0. So this is another tool for evaluating contour integrals. Before this we have seen Cauchy-Ursaert theorem, which says that if our function is analytic everywhere inside and on a simple closed contour, then our answer is 0. Suppose this z0 is outside this C, then this integral will become 0 by Cauchy-Ursaert theorem, and this is integral Cauchy integral formula. And we have seen that if our function f of z is analytic in a simply connected domain, then it will have an antiderivative, and if we are integrating it between any 2 points in that simply connected domain, then value is given by f of z2 minus f of z1. And before this, we have seen the definition of contour integrals. We are considering parametric forms, and we are able to convert our contour integral in terms of real integral, and we are able to evaluate those integrals. So we started with this one by definition, then we obtain this result for analytic functions in a simply connected domain. Then we discussed Cauchy-Ursaert theorem, that if our function is analytic everywhere inside and on simple closed contour C, then integral is always 0. And now we have another tool, Cauchy integral formula, which says that if our function is analytic everywhere inside and on a simple closed contour C, and if z0 is any point interior to C, then this integral is given by 2 pi I times value of this function f of z at z0. So be careful, you have to apply appropriate integral formula according to the conditions satisfied. If your function is not analytic, then you have to go by definition. If your function is analytic in a simply connected domain, then its integral is independent of path of integration, and you can use its antiderivative to find out the value of integral. If your function is analytic everywhere inside and on a simple closed contour, then you can apply Cauchy-Ursaert theorem and your integral is 0. And if your function can be written in this form, f of z divided by z minus z0, where this f of z is analytic everywhere inside and on a simple closed contour C, and this z0 is interior to this simple closed contour C, then you can apply Cauchy integral formula. So we will continue with Cauchy integral formula in upcoming lectures. Thanks for watching.